So what I mean by a probabilistic model of L functions, it's going to be a tool that will help us answer, either rigorously or at least to guess the answer, questions like this. What is the probability distribution of zeta sigma plus IT for sigma fixed and t in the interval capital T to 2 capital T uniformly. And this is a question I can formalize in two ways. I can ask first, what is the limit of the distribution as t goes to infinity? This is a kind of soft analysis formulation of the question. Or I could just ask, what is an approximation for the distribution with error as small as possible? To use this thing, right? So and the first probabilistic model of the zeta function that was understood is the random Euler product. And this is in the case where sigma is greater than 1/2. This was proven by Bohr and Jessen for sigma greater than 1/2. The limiting distribution, the limit as t goes to infinity of the distribution of zeta sigma plus IT is the distribution of a random Euler product over primes, 1 over 1 minus c of p, p to the minus sigma, for c of p independent, identically distributed on the unit circle inside the complex limits. So if you expand out this Euler product, you can think of this as being a random multiplicative function, a so-called Steinhaus random multiplicative function. Or you can just think of it as an Euler product. And so what this is saying, because zeta of sigma plus IT is 1 over 1 minus p to the minus sigma times p to the minus IT, this is saying that p to the minus IT, which are points on the unit circle, behave like independent, uniformly random points on the unit circle in a precise sense. And so this completely answers at least the first part of the question for sigma greater than 1/2. So the sigma equals, no, sigma appears here in the formula. Yeah, so as sigma gets larger, the distribution gets more constant. It becomes more closer, just 1 to 1 with high probability. And as sigma goes to 1/2, this distribution diverges. So there's no distribution. There's no random Euler product distribution on the critical line because this product will diverge with probability 1 for sigma equals 1/2. And then on the critical line, there's a result of Selberg. If we look at the log of zeta of 1/2 plus IT, log of the absolute value for simplicity, and we divide by root log t. Let me do log t, has a Gaussian limiting distribution. So this answers a version of the first question on the critical line. Although the fact that I normalized, I divided by root log t, it destroys a lot of information. Any factor appearing in zeta of size smaller than an exponential of root log t will be ignored by this limiting theorem. There's a version of it for the imaginary, so this is the real part of the logarithm. There's a version for the imaginary part of the logarithm too. It's slightly more complicated to state because you have to figure out how to normalize it properly, which branch to take, but you can do that. And so, but the fact this result is true tells us that for the unnormalized version, if we don't divide by root log t, there is no limiting distribution. It's too large and too small with high probability. So we will only be able to try to attack the second question. Not a limiting distribution, but an approximation for fixed t, where the error of the approximation in some sense should decline. Should decline, should be as small as possible with respect to t. And to go kind of beyond this and get more precise information, we are in the realm of conjectures rather than theorems. And so the model that is needed to make progress on zeta on the critical line is the random matrix model. And so the random matrix model for zeta was initiated by Montgomery. And it was a model not for the values of zeta that I've been talking about over here, but the zeros of zeta. So that I said, he said that the distance, the lim t to infinity of the distribution of the distance from 1/2 plus it to the k closest zeros of zeta should equal the lim t to infinity, sorry, lim from n to infinity of the distribution of the distance from well, let me say the unitary version from 1, a point on the unit circle, to the k closest zeros of a random matrix. Matrix M in the group U of M. So you can do this with either Hermitian n by n matrices, which have real spectrum, and the eigenvalues. The eigenvalues of a random matrix. You can look at so it has real spectrum, the eigenvalues are real, and you can look at the distance from a point in the real line to the k closest zeros. Or you can do, as I've written, a unitary matrix whose spectrum is on the circle, and you pick a point in the circle, you look at the distance to the k closest zeros. Okay, this is not literally true. As I said, you have to normalize by dividing by the average spacing. But once you normalize, this is what he conjectured. And it agrees very well with numerical evidence. There are partial theoretical results in this direction, so, some proved by him and many proved in recent work. This is saying that the zeros of zeta behave like the zeros of a random matrix in the kind of first sense, in the limiting sense as t goes to infinity, and then corresponding a limit as the size of the random matrix goes to infinity. I guess this is rigorously correct if I define distance to be a suitably normalized distance function. Yes? Yeah, so this is a kind of manifestation of universality. It's very different from the kind of universality that we see in random matrix theory, where you take different models of random matrices where the entries have stranger behavior, but sort of are still independent or are mostly independent, and try to show random matrix statistics, because there's no matrix here. There's no, and if there were a matrix, we wouldn't really know anything about its entries, as far as I can tell. So it's a kind of universality, but it's just a very different kind of universality. And one would need kind of very different techniques to prove cases of this. Maybe there's some overlap in techniques, but certainly some of the techniques have to be very different. Since that time, there's been a lot of different work in random matrix models for the Riemann zeta function and for other L functions. I would like to highlight the work of Katz and Sarnak, who did multiple different things. So one thing they did that was important is observe that zeta functions of function fields over a finite field FQ or sorry, I should say here, zeros of zeta functions actually are eigenvalues of matrices. They are eigenvalues of Frobenius on the Tate module of the Jacobian of the curve that you're taking the function field of. That won't be relevant for this talk. But they actually have an interpretation as eigenvalues of matrices. So suddenly in that context, in the function field analog, this type of conjecture can be interpreted as a statement that these matrices behave like random matrices, which is a much more it's a more believable statement. It's a more conceptual statement than to say that something that isn't a matrix behaves like a random matrix anyways. And then they, furthermore, that they can show the matrices behave like random matrices. In the large Q limit, in the Q to infinity limit. Kind of one. So using Delen's equidistribution theorem, you can study the statistics of these matrices, and you can prove a version of this statement with a limit is Q to infinity here, because you have in the setting this auxiliary finite field, you let the size of the finite field go to infinity. And this requires computations of some monodromy groups. And by studying the nature of this result, by studying those monodromy groups, they were able to make additional observations. So they were able to describe, so they had random matrix models. For low-lying zeros. So if you have a family of L functions, you can look at the zeros of that L function near the point 1/2 instead of looking at high up in the critical line. And you can ask what's the distribution of those zeros as the L function varies. And by considering a function field analogy, they realized that you get different answers for different families of L functions depending on its so-called symmetry type. And they're able to make precise conjectures about that. And those conjectures also fit very well numerical data that we have. And various partial progress towards them has been verified in many cases. No, because in the function field setting, so for the zeta function, the function field has a genus, and this number of eigenvalues, the size of the matrix is twice the genus. And so if you fix the genus, the size of the matrix is fixed. But yeah, the zeros do end up getting closer together, which has to do this equivalence. This equivalence involves you evaluate the eigenvalues have to be q to the minus s, where s is a 0. And so as q grows, even if the zeros are the eigenvalues are the same, that makes the zeros get closer together. But the size of the matrix is fixed, and that's a big thing that enables this to work. It's much easier to show something is equidistributed in a fixed space of matrices of a fixed size than in a growing space. However, all this work that I mentioned was only about the zeros of the zeta function of the L function. It didn't say anything about the values of the zeta function L function. And there's a natural there's a natural idea for how you would give a random matrix model for the values of the L function or zeta function. So the random matrix model suggests that zeta should behave like the characteristic polynomial of a random matrix, determinant I minus m for m in un. Rand. So why is this? It's because the zeros of the characteristic polynomial of a matrix are the eigenvalues of a matrix. The characteristic polynomial is the only natural function with this property, although of course there are others you can multiply by an exponential. And so if the zeros of zeta behave like the eigenvalues of a random matrix, then it would follow that zeta should behave like the characteristic polynomial of a random matrix. However, you cannot use this as a model for the value of zeta directly, the way Montgomery did. And the reason is, as you take the limit as n goes to infinity, this doesn't converge to any distribution. But I mean, maybe that's not surprising, because we just saw lim t to infinity doesn't converge to any distribution. And so you shouldn't expect the random matrix model to predict some kind of limiting distribution. So if we want to apply the random matrix model to the values, we've got to consider behavior not in the limit. And so this was done by Keating and Snaith. They said that zeta of half plus it for t random in the interval from t to 2t random behaves like determinant of I minus m for m in un random, where n is close to logarithm of t over 2 pi. So both the distribution of the values of zeta and the values of the characteristic polynomial is diverging as t goes to infinity on one side and as n goes to infinity on the other side. But if we find the right exchange rate between t and n, if we match up the growth of t and n, then maybe they diverge at the same rate, and the distributions actually stay close together, even as they go off to infinity. And then once you have that idea, you can figure out what the comparison should be by matching properties of zeta we understand to properties of random matrices that we understand, and you get this formula that n should be roughly log t. which is funny. I mean, log t is not always an integer. You have to like round to the nearest integer or something. But they, did numerics, matches the data. It matches the data much better than the theorem of Selbach. So it's always good when your conjecture fits the data better than the theorem. And however, there is more we could ask for from a model of zeta. If we have a really good model for the distribution of zeta, it should predict all kinds of statistics about that distribution. Yes?
So you write log of t over 2 pi, and then 2 pi only contributes all of 1 to n.
Yes.
So the normalization in that exact constant, does that just say that when little t is around big T, so not just between t and 2t, but somehow within 1 plus epsilon factor, big T, that's when the...
Yes, yeah. So yeah, so I was vacillating on whether to write this 2 pi or not. I mean, the error in this is going to be of size kind of O of 1 anyway, so it doesn't super matter, but it does seem like 2 pi is the right thing to put in there. But yeah, so there is this t to 2t issue. If you wanted to make it really precise, you would have to choose a smaller interval in t. So that kind of details, those kind of details won't be relevant for the rest of the talk. So you would hope that if we could understand the distribution of zeta, we could understand its moments. What are the moments? This is 1 over t times the integral from t to 2t, zeta of 1/2 plus it, absolute value raised to the power 2r dt. So these are known for r is equal to 1 and r is equal to 2, and not known for r unknown for integer r greater than 2. And you can look at analogous things in other families of L functions, and I could probably go all day listing which progress is known on calculating which moments. So there's lots we know and there's lots we don't know. And so if you had, so a good model for zeta, if you just take your model probability distribution and you integrate this against it, it should give you ideally the right formula for the moments that agrees with what we know, and in every case we can calculate, and extends it naturally to some higher moments. And so for Keating and Snaith, model, you look at like the integral of the determinant of I minus m, absolute value to the 2r against Haar measure. So by the way, is when I'm talking about random matrices, I always mean random according to Haar measure. You could, of course, consider random matrices according to other kinds of measures, but for the first part of the talk, I'm only going to be talking about Haar measure. But for the second part of the talk, it will be different. So you have an integral about Haar measure. This you can calculate. This turns out to be a polynomial in n of degree r squared. And so we expect that the moment should be a polynomial in log t of degree r squared. And the known cases of the moments are, in fact, a polynomial in log t of degree r squared. And all evidence suggests all the moments are polynomials in log t of degree r squared, but it's not the same polynomial. The coefficients of the polynomial are not right if you directly apply the Keating and Snaith model. Now, Keating and Snaith, they didn't just stop there. They explained how to fix this and give the right formula for the moment polynomial, at least for the leading term. So the Keating and Snaith conjectured that the true moment is equal to the random matrix moment times some arithmetic factor, which is independent of t, plus some small error. So error. Where the error just means like smaller than the main term, maybe smaller by a factor of log t. So what is this arithmetic factor? It arises really from the random Euler product model. The arithmetic factor, if you try to calculate the moments in the random Euler product model, well, you can do it off the critical line, but it diverges to infinity as you reach the critical line. So it's like the expectation of the product over p, 1 over 1 minus c of p, p to the minus sigma, absolute value raised to the 2r. You take the limit as sigma goes to 1, which 1/2, which doesn't exist. But if you multiply by sigma minus 1 to the r squared, it exists. So it's a regularized moment of the random Euler product model. And so this arithmetic factor was already identified. The other factor to calculate the moment was missing, and they realized it should be the random matrix factor. And
Sigma minus 1/2.
oh, yes, sorry, sigma is half. Thank you. They realized it should be the random matrix factor, and then they gave a better prediction. So this gives a prediction that agrees with known results up to an error term of 1 power of log t less than the main term. So they can get the leading constant of the polynomial, but not the other constants. But we could try to do better. We could try to get the whole polynomial, predict that. And this was done not using a probabilistic method by Conway, Farmer, Keating, Riemann, Snaith. So let me just write the letters. So CFKRS, the recipe predicted the full moment polynomial. So this is not by making any kind of prediction about here should be the probability distribution of zeta, let's integrate that and get the moments, by some completely separate method where you write out zeta as a sum, you like exchange the sum with the integral. You want to just drop terms that look like they cancel and keep the rest, but that gets you an answer that's wrong. So you do something else, you like add a bunch of extra terms, and then you drop the terms that seem like they cancel, and the extra terms you added are infinitely large, but the infinities cancel, and you end up with a finite answer that turns out to be right. It's very strange. It's a very strange method, but it seems to really give correct answers in every case that we've checked. And there are other approaches to predicting moments. There's an approach of multiple Dirichlet series by Diacono, Goldfeld, and Hofstein, and then there's additional work in that direction. And there's more recent work of Conway and Keating. There's other ways to try to make predictions, but they give the same answer. They always agree, at least up to terms. Maybe some of them, and for some families, will have lower order terms that differ by like a power of t instead of a power of log t. They give the same prediction for the kind of the leading polynomial, and none of them is probabilistic in nature. It doesn't come from any kind of description of the behavior of zeta. Probabilistic. Yeah, well, so I think for the absolute value moments, it doesn't matter so much if you put the gamma factor in, because the the argument of the gamma factor is canceled, and it's only the size of the gamma factor that matters, and then the size of it is smoothly varying. If you did a non-absolute value moments, it would change things. Yeah, but I think it's not a huge difference. And you could say, so the recipe does apply. There's a version of it if I want to do an unbalanced moment with like complex conjugates in it. If I want to throw in a bunch of gamma factors, you can apply the same ideas to give predictions. And then like you could say, I'm going to throw in more copies of the gamma factor than I need to complete the L function if I want. Or I think so. Or because for L functions there's like the epsilon factor, and then that's kind of the more relevant thing. Throw in more copies of the epsilon factor.
You were pointing out that random matrix version of the recipe that matches up kind of with.
Yes. So you can use, so the recipe is derives from, or was discovered at kind of at the same time as, a specific method to calculate these moments for random matrices, which I wrote somewhere over here. The moments of random matrices, you can compute it by a strategy that looks very similar to CFKRS. So in that sense, CFKRS is justified by random matrices in that we apply the same procedure which works rigorously in the random matrix model to do it non-rigorously for the zeta functions. But it doesn't come from the random matrix model in the sense that we translate a question about zeta into a question about random matrices. That's a good point. And so there's one more probabilistic model of zeta functions that I will talk about in prior work, which is the work of Gonek, Hughes, and Keating. And this work starts with a theorem, the Euler-Hadamard product, that zeta can be written as a product of some Euler factors times some Hadamard factors times 1 plus little o of 1. So the zeta function is written as an Euler product over the primes. And like any reasonable holomorphic function, it can be written as a Hadamard product over zeros. And so the observation of the Euler-Hadamard product is that if we take only the most important primes, which are the smallest primes, and we take only the most important zeros, which are the zeros closest to the point we're trying to evaluate the function, we can make a modified product that still gives a very good approximation to the Riemann zeta function. And so ideas like this recur in number theory. The approximate functional equation is another version of the same idea. And then, so the idea is we combine the random Euler product model and the random matrix model. We model the Euler factors as independent random. And I mean, this can be made even rigorous. And the Hadamard factors as or with zeros. So the factors depend on some zeros, and the zeros should be the eigenvalues of a random matrix. So this gets you a different way to probabilistically model the value of zeta. And if you take this model and you evaluate what it predicts for the moments, you get exactly the product formula of Keating and Snaith, of a random matrix factor times an arithmetic factor, which is unsurprising because the moments of a product of independent random variables are the product of the moments. And so if I model it as a product of these two different factors, the moment formula should be a product of the terms of the two types. So that means the Gonek-Hughes-Keating formula give a probabilistic explanation for the leading term of the CFKRS polynomial, but not a probabilistic explanation for the lower order terms. And so they raised in their paper the question of, can we probabilistically explain? Can we give a probabilistic model predicting all terms? So the answer I'm going to talk about today is yes, with some caveats. So the first is, I'm not doing this model in the setting of the Riemann zeta function. I'm doing it in the setting in a function field analog. And the second is, the function was over a finite field, and I need to take Q sufficiently large in terms of the moment. And the third is a small caveat. This is a work in progress. I didn't quite finish an archivable version in time for this conference, but it is version suitable to be sent to experts. So if anybody wants me to send it to them, I would be happy to. Get all the way up there. So what I want to do in the remaining time is to first say what my function field analog situation is, and then say what the random model is, and then state some theorems about it. And then if there's a little bit of time, I might say something about the proof. Does anybody have questions about what I said so far? So to make my random matrix model, I want to make the following observation about the zeta function. About, well, let me write it like this. Zeta of s plus it is equal to the product over p, 1 over 1 minus p to the minus s times p to the minus it. And so this can be expressed in terms of the function n goes to n to the minus it. And what property does that function have? First is it's completely multiplicative. So the value on a product of n is the product of values. And then the second is n to the minus it can be approximated given the number of digits of n and the leading log t digits. This. So I'm going to consider functions on polynomials over a finite field that have analogous properties. So I'm going to use the following system of analogies. I'm going to have FQ, finite field, with Q elements. So you can just think of this as being the integers modulo P for a prime P. FQ of U is the ring of polynomials. I'm going to think of this as analogous to Z. FQ of U plus is monic polynomials. These are polynomials whose leading coefficient is 1, and I think of them as being analogous to the natural numbers, for example, because they parameterize the ideals of, or the non-zero ideals of this ring. And I'm going to say pi in FQU plus is prime if it's irreducible. So if it has no monic factor, if it's not 1 and it has no monic factors other than 1 in itself. And the analog of the size of a number, the size of a polynomial, is given by q to the degree f. So it should be analogous to the absolute value of a number. And so I guess for this explanation, I should say also the coefficients of a polynomial are analogous to the digits of n. So I'm going to consider a function chi from FQU plus to the complex numbers, or let me say even to the unit circle inside C, which is completely multiplicative where chi of f is completely determined by the degree of f and the leading n plus 2 coefficients. But not for n plus 1. And then I could consider LS chi to be the product over pi prime, 1 over 1 minus chi of pi, q to the minus s degree pi. So chi is going to be an analog of n to the minus it. The fact that it's completely determined by the leading coefficients instead of approximately determined is just because in function fields many things are exact instead of approximate. It's easy to see that any function which is approximately determined, in this case, would be also completely determined. Okay, the plus 2 there is just to make the formulas that appear later nicer. And you can think of n as being so you can think of these as being characters of the Adele class group that are ramified only at infinity, and then n would be like a kind of global, yeah, it was related to constant global functional equation. But yeah, just n plus 2, and then I'm throwing out the ones with can be determined by n plus 1 coefficients for the same reason I consider only the dyadic interval from t to 2t. I'm throwing out the ones from 0 to t. And this Euler product is a direct analog of the Euler product for zeta of s plus it. And then we have in this setting the random Euler product model, which will involve an Euler product LC associated to a function c of s is the product over pi prime, pi and FQU prime, 1 over 1 minus c of pi, q to the minus s degree pi. And we'll take, so we consider LC independent identically distributed on the unit circle inside C. So there's a random Euler product model in this setting, which looks very similar to the classical Euler product model. Ah. So some people. And then there's also a random matrix model. Oh, I don't even have to erase that part. Model. So I'll write Lm for determinant of I minus m q to the minus s for m in un. So this comes with a theorem, which in this case is due to V, which is that L chi s is equal to Lms, well, L chi dot as a function of s is equal to Lm for some m. So the exact details like the +2 and the not +1 here are what's needed to make this theorem true. And so that theorem then motivates a model. The random matrix model is we consider Lm for m in un har random. Har random. So I haven't checked, but I believe that pretty much everything that I said about the two models, how they relate to zeta by theorems, by conjectures, it will still work in this setting. So the Euler product model will be a good model off the critical line. The zeta, the Mandarin matrix model models the values reasonably well on the critical line. There's an analog of the Gonek Hughes Keating model that does it better. This stuff has been checked in function fields for some families of L functions, not for this specific one probably, but the same arguments should go through. So again, we face the question, how do we do better? And here, there's a kind of natural starting point to do better. Well, I know that the L function definitely comes from the corresponding of a random matrix. Let me find a different measure on un other than the Haar measure and consider random matrices according to that measure. So we just have to figure out what the measure should be. And the goal would be to get a measure that correctly predicts the moment polynomial. But that I think that in figuring out what the measure should be, it's not a good idea to start there. It's a good idea to start with a different observation. Ls chi is always equal to Lm for some m, and it equals Lxc for some xc. So both models are accurate in how they constrain what our L function can look like. It has to look like it came from both of them. So therefore, that stands to reason that our measure should be supported only on matrices that give us L functions that satisfy both of those properties. So we want a measure supported on, well, when I say it is the intersection of the supports of these two distributions. So how do we write down a function whose support is an intersection of the support of two functions? Well, the simplest thing we can do is multiply them together. So we can try to multiply these probability density functions. Now this seems really weird because what does it mean to multiply probability densities. I mean, you can multiply probabilities if you have independent random variables, but that's not what we're trying to do here. And yes. So what we're going, so roughly what I'm going to project them to the same space. For example, to look at the first few coefficients and multiply the probability densities there. I'll give a formal statement in a second. Yeah, and yeah, I want to kind of multiply their probability densities. So, but multiplying densities is a bad idea. It depends on my choice of coordinates. So I can fix that if I divide by a third density. And then there's a very, very natural choice. So both the distribution of Lm and the distribution of Lc approximate in the limit, and they converge to in some kind of limit, a Gaussian distribution, a distribution of random power series whose coefficients of their logarithm are independent Gaussians. So and it's the same Gaussian distribution in each case. And so as Q gets larger, this gets closer and closer to Gaussian. As N gets larger, this gets closer and closer to Gaussian. And we want our new model to have the same property. It should go to a Gaussian as long as Q and N both go to infinity. So to preserve that property, we want to multiply them and then divide by the Gaussian. And so then as one goes to the Gaussian, it'll converge to the other, and the other goes to the Gaussian, it'll converge to the one. Or another way of saying that, like if we didn't divide, we have two things that approximate a Gaussian. You multiply them together, you get the square of a Gaussian. The square of a Gaussian is a Gaussian with half the variance. But there was no logical reason to divide the variance in half. We divide by the Gaussian, and then we don't divide the variance in half. So roughly, we're going to multiply the PDFs. So a more convenient way to make that mathematically precise is to multiply one measure by the PDF of the other, because that's an equivalent statement. So what I'm going to do is define random variables x1 c up to xk c. Okay, my x's are getting just more and more like random squiggles. By the formula, the L function of xc of s should equal e to the sum k equals 1, or n equals 1 to infinity, xn c, q to the minus n's. So I want to extract the coefficients of the logarithm here, and I'll call those my variables xn. And so I'll define a function f in k complex variables fk to be the PDF, probability density function, of x1c up to xkc. Where k is a weird auxiliary parameter. I'll say more about that in a second. And then we'll define, this is where I have to check my notes to make sure I'm writing my formulas correctly. Mu weighted is a measure on the unitary group to be equal to gamma times f of minus q to the 1/2 trace of m minus q to the k over 2 trace of m to the k over k divided by a product from n equals 1 to k e to the minus trace m n squared over n times n over q to the n pi times Haar measure, where gamma is chosen to make this unique constant that makes the total mass 1. So what have I done in this formula? I start with the Haar measure, and I multiply by the PDF of this x1 through xk distribution. Where am I evaluating this PDF, I want to evaluate the coefficients of the logarithm of Lm. So if you calculate the logarithm of determinant I minus m, oops, there should be 1/2 up here. 1/2 minus s is the correct formula there. You calculate the determinant of I minus m q to the 1/2 minus s. For the logarithm, the first coefficient is minus q to the 1/2 times the trace. The kth coefficient is minus k over 2, trace of the kth power, divided by k. So you just plug those in, and then we're going to divide by the PDF of a Gaussian, which is going to involve taking the trace of the nth power, absolute value squared in an exponential. We divide by n because that's the right variance to use for the Gaussian, and then we multiply by, this is the correct constant to put in front. We multiply that by mu har, we get a measure on un, which is non-negative, it's non-negative, it's not a signed measure, but it probably doesn't have total mass 1. So we just have to multiply by a constant to make total mass 1. Now it's a probability measure. So the model LS chi should behave like Lm for m distributed according to the measure mu weighted. I have weighted the Haar measure by the probability density function of this random Euler product measure so that it now has properties of both the Euler product and the random matrices. Is there a question? No. Okay, and so let me state the main theorem of this. If I look for what the prediction for the moment should be from this model, that's the integral over un, determinant of I minus m, absolute value to the 2r against mu weighted. This equals the main term predicted by CFKRS, the appropriate analog of CFKRS, plus O of, oh, okay. Q is fixed. Yes, sorry, Q is fixed. The other thing I should have said is that K is equal to n to the 1/2 minus little o of 1. And what I probably should do here, the better definition is to take limit as K goes to infinity. But that is more analytic work, and this is easier. In particular, I didn't check that the limit as K goes to infinity exists. But yeah, so K is some weird auxiliary parameter. You shouldn't worry about it too much. I can say more about that. Q is fixed. And the error term is O of n to the 2r squared minus q minus 2 over 8 plus little o of 1. This is for q greater than 11. Fixed, and then r is fixed.
1r squared?
No, I mean 2r squared. Yeah, so I would like it to be r squared, because then as soon as q is greater than 11, I would get at least the leading term here bigger than the error term. But because of the nature of the proof that I have, it's 2r squared. So the leading term is of size n to the r squared. It's a polynomial in n of degree r squared. And so to get the error term smaller than the main term, I need to take q larger than 16r squared plus 2. However, if I take q just a little bit larger, up to 32r squared plus 2, because I have a cube minus 2 over 8 here. So 32r squared plus 2, the error term becomes little o of 1, and I extract all coefficients of the polynomial. And so this error term, this is another thing. So there is a number of things about this that I hope that someone will be able to improve. Like, I think that the method is not sharp, and the same theorem will be true with a smaller error term. And so ideally, this will be true for smaller values of q. I also think this should be true for other families of L functions. But for now, I just want to state it for this one family of L functions with this kind of large error term that for q reasonably large, I mean just only quadratic in R, it will be little o of 1, and we'll extract the whole moment polynomial. Okay, are there further questions about this statement? Okay, so I should probably stop here because, I mean, I started a few minutes late, but yes. Great, thank you for inviting me to speak.
Thanks very much for beautiful talk.
I think I missed why. So when we construct this random L function on the far left board, so we're still in characteristic 0. This is complex values. Are there going to be, so it looks like there are finitely many coefficients that you can take arbitrarily on the circle, and then those determine all the others?
There's infinitely many primes, so there's infinitely many coefficients on the circle for this random polar product model.
But I mean, the chi is completely multiplicative and determined by finitely many coefficients.
Oh, for chi, I mean, yes. So I mean, chi. I mean, it's like so. I mean, the set of possible values for chi is a finite set of circles, and I'm choosing a kind of reasonable uniform measure on that finite set of circles. So I'm modeling a distribution on a small set, but I'm modeling it by a distribution on a much bigger set, and that's what enables me to compute the moments for the model distribution, whereas I cannot compute the moments for the original distribution.
Let's say take psi of I believe.
Oh yeah, sorry. Take xi of yeah, xi of pi IID. Thank you. Yeah.
In the recent work of they in the moments is you have a interpretation in the topology because they have to also match all these coming from topology. Do you have a
yeah, so I would have said something about that if I had like 5 more minutes. So let me say a very brief version, which is the method of proof of this involves decomposing this function as a sum of characters of irreducible representations and calculating the average against this measure of characters of irreducible representations. And the formulation, the real theorem that implies this theorem is a formula for the average of characters of irreducible representations, of which some of them cancel, the averages are small, and some of them agree with averages against the multiplicative function measure. And so that dichotomy is something that was previously observed as a naturally arising from geometry. It would naturally arrive from the cohomology vanishing statement. So both in my earlier work and in the work of Bergstrom, Diacono, Peterson, and Westland. And so that idea is natural from a kind of topological perspective, and that what I'm showing here is that it's natural also from a probabilistic perspective. And in this case also it implies a CFKS-like heuristic. So that's the connection, kind of. Yeah. Oh.
So this is all in terms of unitary.
Yes.
Would it be different if you use
So
particle or more relevant for curves of?
yeah, you cared about you care about zeta functions with curves over finite fields. So, well, at the minimum, you have to do all the calculations in my paper over again in a different context. My paper also uses, crucially, a paper of Johansen and Lampert about in just the classical random matrix theory of the unitary group. And I think you would have to redo their paper too, or maybe I don't know, maybe a symplectic version of their paper already exists. So I think it should work. You would have to write pages and pages and pages. It's about the distribution of these coefficients having Gaussian distribution in a very strong sense. Okay, great. So that part is good. So just my paper you would have to redo. And probably it would work, but I didn't do it, so I can't say for certain. There's another difficulty, which is it's really helpful to me that this distribution is continuous and not discrete. If you're thinking about curves that are finite fields like hyperelliptic curves, you'd have a discrete distribution here. I mean, so this wouldn't have a PDF. You have to do something slightly different. That would add additional analytic difficulties. I think it can be done, but I can't say with certainty. So in my arguments, the work combines theorems only about this model with theorems only about the random matrix model to produce theorems about the combination. And so I reason as little as possible only in the combination because it's easier to do work on one side than the other. And so the steps where I kind of combine them, I combine ideas from the two sides, are uniform and would work equally well for other groups. The Johansen-Lambert stuff works equally well for other groups. So then the only issue is the stuff where I do analysis on the local Euler factors to redo that. But so it's not really, the group it would not be the obstacle to generalize this to other families of functions. So it should work in all symmetry types, at least if the local factors are nice enough. So for example, something like a distribution of modular forms where I have a Plancherel measure locally would be easier for me to handle than quadratic characters because of the continuity.
Yeah. So here is genus is 0, right? So what happens if genus is positive?
For what I am doing, for this family of characters, you could give an analog of this family of characters in higher genus. You would do characters of the Adele class group ramified at only one point. For what I am doing, it makes very little difference. Like I have some estimates involving the number of primes of a given degree, and those would have a bigger error term if the genus was higher, but that's the only thing that would change. Because I'm not actually proving a theorem about L functions, I'm proving a theorem relating two models of L functions, which both require thinking locally at key steps. Kind of most of the difficulty is local, and it would transfer over to the genus case. Not with the same role. It probably would end up hiding in the little of 1 here. It would not be a big difference in terms of the error. Oh no, that's not quite true. It depends. So degree 1 primes specifically are very dominant for the source of the error term, which is kind of weird. And so it would really matter exactly how many low degree primes your higher genus curve is. So if you don't know anything about the number of low degree primes, I'm sorry, G would occur in the error. You would have like a Q minus 2 root G, 2G root Q instead of a Q here. But then if you know that your curve has more than the minimum number of points, then you would have a better error term.
Let's thank Will again.